Hi everybody, welcome back. In this video we will focus on learning about energy changes in solution formation. In the last video we really focused on reviewing intermolecular forces and how they play a role in determining if something will be soluble or insoluble in a particular solvent. But now we want to focus on the energy associated with the dissolution of a solute in a solvent. So, in order for a solution to form, you must separate the solutes. You got to overcome their intermolecular forces. And as always, I always tell you to draw it out to help visualize the process or maybe the reaction that's taking place. But right now we're talking about dissolution, so we're just talking about a process here. And there we go. So separating out the solvent. Now, do you think this process is endothermic or exothermic? Right, it's an endothermic process. Because energy is required to overcome the solute-solute interactions and when we think of something that is endothermic, would you say that is a favorable or a not favorable process? Right, it's not typically favorable. Good. All right. So another thing we have to consider when we are dissolving something is that we got to separate out the solvent. Those solvent particles really like each other, right? So initially they're really close together in my beaker, but in order for a solution to form, we got to separate out, overcome those solvent-solvent interactions. And so this process too would be considered endothermic. Because energy is required to overcome the solvent-solvent interactions. And so once again, not super favorable. Because the solvent particles like one another, like themselves, right? And so we could write the enthalpy of the solute, since it is endothermic, will be greater than 0, and the enthalpy of the solvent will also be a positive number greater than 0. Now, when we mix the solute and solvent together, so we have the solute plus the solvent, and if they mix together, and that solvent dissolves the solute, this process is actually exothermic because the energy is released as the solute particles interact with the solvent. In this process, if it's exothermic, is favorable. And therefore, you could represent that as the enthalpy of mixing would be less than 0. Because anytime you think of exothermic, you think of a negative delta H. All right, let's continue on then with that thought. Remember back in first semester general chemistry, you would have learned about Hess's law. And basically that states that the enthalpy of solution or reaction, if you're studying a reaction, but in this case the enthalpy of the solution is the sum of the changes in enthalpy for each step. So therefore, to calculate the enthalpy of solution, that will be equal to the enthalpy of the solute plus the enthalpy of the solvent plus the enthalpy of mixing. And therefore, the enthalpy of solution is dependent on the magnitude of the individual enthalpies. So let's look at a figure here that summarizes what's going on for if you have an exo versus an endothermic process taking place when dissolving a solute into a solvent. Now, I just want to briefly remind you of energy diagrams. So when you studied thermochemistry in first semester general chemistry, you would have learned a little bit about energy diagrams, and usually we teach it in the simplest form. We have energy on the y-axis and, for example, reaction progress on the x-axis, and they would have looked something like this, where R stands for reactant and P stands for product, and you had to get over an activation barrier to get to the product. And that because the products were higher in energy than reactants, then this would have represented an endothermic reaction. And so the enthalpy of reaction here would have been positive for endothermic, because you do products minus reactants, right? So this would have been endo. And then an example of exothermic would be the reactants being higher in energy than the products. Energy, and this is the exothermic example. And that's because when you do products right minus reactants, you would have gotten a negative enthalpy for that reaction, right? So you may remember products minus reactants, products minus reactants. That will be useful to remember when we dive into thermo again in the future videos together. So just wanted to remind you of that. And later on, if you want to take more chemistry, you will learn that energy diagrams are typically not just one step. When you're doing a chemical reaction, they can be many steps. But in this case here, this whole principle can be applied to what you're looking at here. Imagine these as just big energy diagrams, and we're not doing a reaction, we're just trying to make a solution, right? So your reactants here, You can treat them as the solute and the solvent, and then the solution is your product. That's your end goal here. And so on the y-axis is energy, and on the x-axis is just dissolution, right? Trying to dissolve. Okay, so trying to tie it back into stuff that you may be familiar with. So let's go ahead and discuss what this figure shows us, because there's a lot of cool visuals here. So in this case here, we start off with our solvent and our solute. And here you see the enthalpy of the solute. So there's a certain amount of energy required to break up the solute particles. And there's a certain amount of energy required to break up the solvent, right? And eventually they're separated, and then we mix them together. And remember that the energy of mixing is highly exothermic. So if the magnitude of the enthalpy of mixing is greater than the magnitude of the sum of the enthalpy of the solute plus the enthalpy of the solvent, then when you do products minus reactants, you end up with an exothermic solution, right? Which kind of represents what we see over here in that energy diagram. Whereas if the magnitude of the mixing is less than the sum of the magnitude of the enthalpy of the solute and enthalpy of solvent, then we see a situation that looks like this scenario here, where if you did products minus reactants, we get a net endothermic process, which isn't as favorable as an exothermic process energetically. Let's look at this explanation. So what I just showed you in that figure, I'm going to explain mathematically here on this page as well. So anytime you see these brackets in math, they stand for absolute value, because we understand now that enthalpy can be positive or negative depending on if it's endothermic or exothermic. But as you just heard me discuss on the figure, I'm looking at the order of magnitude. And so that's the reason why I'm taking the absolute value of those, okay? All right, so let's say hypothetically they're equal to one another. Then if you did products minus reactants, then you would get an enthalpy of solution that's approximately 0. Now, will this actually dissolve? Will it go into solution? Well, remember in the previous video I talked about that based on the second law of thermodynamics, the universe wants to go towards disorder, which means that these solute and solvent, they want to mix. You know, not all can dissolve, but nature has a tendency towards that, to spread the kinetic energy of the particles over a greater volume. So the entropy of mixing will always increase, right? That's the drive forward. And that will drives the formation of solution, while the energy of the system, which we're referring to as the enthalpy of solution, the system is a solution, remains constant. And so that's where we saw the enthalpy of solution is approximately 0. It's constant, right? It's not favorable. It's not favorable. It's just, not really helping to drive the formation of the solution, but the entropy will. The second law of thermodynamics does help it out. Now, let's say we have the enthalpy of the solute plus the enthalpy of solvent is much less than the enthalpy of mixing in terms of magnitude. Then that's when we got an enthalpy of solution less than 0, and that was that exothermic process, which is favorable. And so having a negative enthalpy of solution and that entropy of mixing increase due to the second law of thermodynamics will drive the formation of solution. And so you can be confident that if you have this scenario here, the solute will be soluble in the solvent. All right, now if you have the opposite situation where the solute and solvent is greater than the enthalpy of mixing, then if you did products minus reactants, then the enthalpy of solution is greater than 0. We have an endothermic process, which is not favorable. It's not to say that mixing will not occur, as long as the enthalpy of the solution is not too large the tendency towards greater entropy drives the formation of solution. However, if the enthalpy of solution is large, then a solution will not form. So all those solubility rules you would have learned in first semester general chemistry and you're reviewing over now for this chapter are based on a lot of this is data here. You can look up literature data and theoretically calculate if a solution will form or not. And it also, we'll discuss this in a later video, it's also temperature dependent as well. So there's several factors you have to consider to decide will something go into solution or not. Okay. Now, since we're working in a general chemistry course here, we're mainly working with aqueous solutions. And so many compounds or many solutions contain an ionic compound, and that is usually dissolved in water. And so we can simplify this equation to solve for the enthalpy of solution. The enthalpy of solution is equal to the enthalpy of the solute plus the enthalpy of solvent plus the enthalpy of mixing. The enthalpy of solvent plus the enthalpy of mixing, we can simplify as the enthalpy of hydration. If you're in the scenario where you have an ionic compound dissolved in water, okay? If you don't, if it's an organic molecule dissolved in organic solvent, then you would just use this equation here. But if it's an ionic compound dissolved in water, then we can simplify it to the enthalpy of hydration. That is defined as when you have 1 mole of ions dissolved in water. And there's literature data that you could look up for specific ionic compounds. This particular value is large. It's a large value, and it's exothermic. Now let's come back to ionic compounds. We'll get back to hydration later, but let's come back to ionic compounds. And remember that they're composed of a cation and anion. And you would have learned about this concept of lattice energy. I just want to review over this with you. It's the measure of energy released when ions are combined to form a compound. It is the measure of the cohesive forces that bind ions. So So basically, it's what holds the ionic compound together, this lattice energy. So for example, if you had sodium chloride, we know you have alternating sodium cations and chloride anions, and what's held together is that electrostatic attraction. It's very strong. And the reason why sodium and chlorine are attracted to each other is because then they can exchange an electron. Sodium gives up its extra electron so that the chloride and the sodium both achieve a noble gas configuration. So a lot of energy is released. And so you can imagine that the enthalpy of the solute, what we were talking about here, what we need to break apart, is just opposite of what holds it together. And that's why this is positive and this is negative. It's just saying they're equal but opposite in value. And so basically you can find numbers for the lattice energy for ionic compounds. And so it just depends what you find in literature on your word problem. The enthalpy of solution is equal to the enthalpy of solute plus the enthalpy of hydration. Or if you have the lattice energy, then you can do a substitution here and say, well, the enthalpy of solution is equal to the negative enthalpy of lattice plus the enthalpy of hydration. So it just depends what you have available. I'm going to focus mainly on the enthalpy of the solute for right now. If it is less than the enthalpy of hydration, then that, you remember this is a highly exothermic process. So overall, this would be exothermic. Definitely favorable to overcome that. And an example of that would be lithium bromide. We learned from the solubility rules that lithium salts are soluble in water. And so this definitely dissolves into ions, the lithium cation, the bromide anion, and actually if you were to look up the literature data, the enthalpy of solution is negative 48.78 kilojoules per mole. Definitely highly exothermic. And actually this is really important in terms of safety. Whenever I would prepare sodium hydroxide solutions for my research, sodium hydroxide, when you purchase it, comes into little pellet form. And then when you dissolve it in water, it's actually very exothermic, that dissolution. And so I would always prepare it in a large Erlenmeyer flask. Typically, I was making a lot of it. And I would put it on ice to help control the energy that was released, because it can be quite dangerous if you're working with something very exothermic. So in terms of safety reasons, it's important to do these types of calculations so that you do not injure yourself or someone else. And you can take the necessary precautions to avoid an accident. All right, so what happens if the enthalpy of the solute is greater than the enthalpy of hydration? Then that means we're working with an endothermic type process here, where the reactants are essentially lower in energy than the products, right? So endothermic. And an example of that would be silver nitrate. Now, we learned also from the solubility rules that silver nitrate or nitrates are soluble in water. And so this one does dissolve. And so when we look up the data for the enthalpy of solution for this specific ionic compound in water, it's a positive 36.91 kilojoules. Now, that's not favorable, but what does push this specific ionic compound to dissolve in water? Excellent. It is entropy. The entropy of mixing will help to overcome this endothermic process here. Remember, nature wants to go towards more disorder. All right, and then the last scenario, what happens if they're approximately the same? Then that means the enthalpy of solution is approximately 0, and then the example of that is actually sodium chloride. We know sodium chloride is soluble in water to break up into the sodium cation and the chloride anion, and the enthalpy of the solution is approximately plus 3.88 kilojoules per mole. And we know it goes into solution, so it definitely entropy of mixing is driving this forward. All right, let's do a practice problem together. In this question here, it tells us that potassium nitrate has a lattice energy of negative 163.8 kilocalories per mole and a heat of hydration of negative 155.5 kilocalories per mole. How much potassium nitrate in grams has to dissolve in water to absorb 1 times 10 to the second kilojoules of heat? So let's write what we're given. We are given that the lattice energy is equal to negative 163.8 kilocalories per mole. We're also given the enthalpy of hydration is equal to negative 155.5 kilocalories per mole. And we are asked to find the grams of potassium nitrate. What's the formula for potassium nitrate? Excellent, KNO3. Good. And to find grams, we need to solve that. First, we need to find the moles. Then we can go from moles to grams. We are also given that the water is absorbing 1 times 10 to the second kilojoules of heat, and the variable we use for heat is Q is equal to 1 times 10 to the second joules. And when something, we can calculate heat from the formula, the moles times delta H. We discussed that when we were looking at phase changes, so enthalpy of vaporization or enthalpy of fusion, but in this case here we can use the enthalpy of the solution. And we know that we need to find moles, and it looks like we're probably going to find it from using this formula here. Always identify what you're given and what you need. And so it looks like I'm given the Q, I can calculate delta H, and I want to solve for N. All right, so we're talking about making the solution, and so it looks like we need to calculate the enthalpy of the solution, and we just learned that formula together. That will be the negative enthalpy of the lattice energy plus the enthalpy of hydration, which is equal to negative times the negative is a positive, so 163.8 kilocalories per mole plus a negative 155.5 kilocalories per mole, and that's equal to 8.3 kilocalories per mole. Now, always be mindful of your units. It looks like we are, and let me correct my answer here. We were given that it was actually kilojoules, not just joules. So let me fix that for you. So we were given that that was in kilojoules, but we have kilocalories here. So we need to do a unit conversion, and there are 4.184 kilojoules is equal to 1 kilocalorie, just like you probably have learned in the past first semester general chemistry that there's 4.184 joules in 1 calorie. So let's go ahead and do our conversions here. So we have 8.3 kilocalories per mole, and for every 1 kilocalorie there's 4.184 kilojoules, and so kilocalories cancels out, and we have 34.7272 kilojoules per mole. Remember, I'm not going to round to correct number of sig figs until the end, but I will underline that this would have been rounded to 2 sig figs based on the 8.3 kilocalories per mole. All right, so let's continue on. We have Q is equal to N times delta H, and in this case we're talking about a solution. We're not talking about vaporization or fusion here, so it's a solution. And to solve for moles, that will be Q over enthalpy of solution. So you'd have to rearrange the equation. Just plug and chug now. So when I calculated, I got 2.879587 moles. And this is of the potassium nitrate. Have to multiply by its molar mass. And so that moles cancels out. Over here, kilojoules actually canceled out. And when I calculated it, I got 291.126 grams. But remember that we had two significant figures, so the final answer should be to 2 significant figures. So this would be 290 grams of potassium nitrate. Make sure you write down the identity of the substance you're working with. And so that is your final answer, rounded to 2 significant figures. All right, so let's just summarize what we did here. We were provided the total energy for the whole process, and so remember you can calculate heat energy from the moles times the enthalpy. We then had to find the enthalpy of solution from this formula. Given the literature data for the lattice energy for potassium nitrate and the enthalpy of hydration, which remember was 1 mole of those ions dissolved in water, so you can look that up in the literature. So we got the enthalpy of solution to be 8.3 kilocalories per mole, which is an endothermic process. We converted that to kilojoules because the heat energy measured was in kilojoules, so we want to make sure we're consistent with our units, which when we did Q over enthalpy of solution, we figured out how many moles of potassium nitrate were dissolved in order to give off that much energy, and then we multiply it by the molar mass to get how much grams we needed to dissolve and the water to absorb. I did not mean to say to give off, but to absorb 1 times 10 to the second kilojoules of heat energy. All right. Thank you all for watching, and see you next time.